So we can start. Look, we continue with the lecture. So I don't know what about next class, because it seems that we have again problems with the coronavirus and the virus, right, and so on. So let's see. Maybe we'll have class here, maybe online. No idea. If we have class here, yes. If we don't, then we won't test tomorrow, because I already designed the test in such a way that you have to write it here. Because if you are going to write that at home, I will have to create a new test.
How about people who are online?
They have a different test, I think. Yeah, so let's see about that. Okay. So we finished with, we started with the n-dimensional distributions, right? So n-dimensional distribution. And so we already know that in that case we have, so if before we had the Boyle sigma algebra, now we have the Boyle sigma algebra, but on the following set. So we have the Boyle sigma algebra on the space, Rn, and I told you that this is the minimum sigma algebra generated by the following set. We have P1, P2, Pn, where like this, where Pi is just a whole sigma algebra and R. Okay, so we have the Cartesian product of one-dimensional Boyle sigma algebras. Well, of one-dimensional Boyle sets. So we have one-dimensional Boyle sets. P1 to Pn, these are one-dimensional Boyle sets, and we have the Cartesian product, right? Then we will have, if we have here P1, this is P3, then the Cartesian product is squared over here, right? But this is just on the plane. But if we are talking about the space, then we have space, right? N-dimensional plane. And what here we're talking about not only this square, but also we're talking about the minimal sigma algebra that contains this Cartesian product. Then we also have things like this, for example, or in general, any figure, any here like this, right? This is going to be a Boyle set on the space. That means that we can find the probability that the random vector is going to be here. Yeah. Right? Good. So this is the Boyle sigma algebra from our N, and then we define that. What do we define? So we can find. That's right. Yeah, so we can define this function. So this is the distribution. So before we had the distribution, and it was a function from the Boyle sigma algebra on R, and this is going to be a function from the Boyle sigma algebra on Rn. Right? So this is the probability distribution. And for this probability distribution, we can also define the CDF. So this will be the n-dimensional CDF. So F, and before we had f of x, but since we don't have only x now, but we have, we are talking about space, so we have x1, 2, xn. Right? And this is the probability that if we have, so like the meaning of this is that if we have n random variables, So if we have n random variables, we want to know the probability that each of these random variables is less or equal than this than x. So this is just the probability of minus infinity to x1 and minus infinity to x2 up to minus infinity to xn. Right? So this is the definition of the CDF in this case. And we can look at the properties of this CDF. And the first property somehow is the analog of the property in the one-dimensional case when we have that it's continuous. No, sorry, not continuous, but so the first property is that is non-decreasing. So the first property in the one-dimensional case is that the CDF is non-decreasing. And in this case, we have to make sure of the following. We have to make sure that for every possible Borel set like this, the measure, so the probability of this is going to be greater or equal than 0. So the area of every possible figure is greater or equal than 0. This is the same of, yeah, just like that. So because the probability is always greater or equal than 0, so it means that the area, and area in this case means probability, so the probability has to be always greater or equal than 0. And I gave you the following example, right? So if we have some random variable psi and we have another random variable eta, and psi was the number of boys in the group. So if we have here 1, we have 5, here we have 2, and here we have 9. So here we have many points. Well, not many points, but this is some discrete case. So this, each, for example, this point here means that there is 1 boy and 2 girls in the group, right? And then we want to find the probability that there is between 1 and 5 boys in the group, and between 2 and 9 girls in the group. So each of these points is good for us, because in each of, for example, in this point, how many boys are there? Are there 5? There are 5, and there are 9 girls. So this point is good, right? And every point in here is good. So we need, if we want to find the probability that there are from 1 to 5 boys and from 2 to 9 girls in the group, it is the area of this, right? Well, the area. In this case, since we're talking about a discrete case, is the number of points here, right? How many points do we have here? Well, here we have 7, right? Well, 7? No, 8, right? 1, 2, 1, 3, 4, 5, 6, 7, 8, and 9, right? So 1, 2, 3, 8, right? And here we have 5. So how many points do we have here? Yes, right? So 40, right? 40. Yeah, this is the area. Well, this is the number of, yeah, this is like the area for us, 40. And we have to divide this area by the total area of the plane. Let's say, well, in this case, I don't know if the total area is like this, then we divide it and so on, right? Yeah. So, and then we have to make sure that every possible square is greater or equal than 0. And I told you that this means that we have to define the following. Let me write that over here. It means that for every A1 less than B1, A2 less than B2, and an less than bn, we have that delta 1 of a1 b1, delta 2 of a2 b2, up to delta n of b of a n bn of this function has to be greater or equal than 0, right? Yes, this is the first property. So it means that the area of this should be greater or equal than 0, right? So, and if we are talking about, so if n equals 2, so if we are on the plane, then we have the following. We have that delta 1, a1, b1, delta 2, a2, b2 of f of x1 and x2, right? This is what we can draw this here. And we can see that we have here a1, we have b1, a2, and here we have b2. And this means this area. Right? And to find this area is equal to f of what? F of first b1, b2 minus f of a1, b2 minus f of b1, a2 plus f of a1, a2. So in the case of, so if we are working on the plane, then this formula gives us this. And this is just this area, right? Just like this. Let me remind you still that, okay. Just, okay, that this f of b1, b2 is all this, or all this area. Okay. Yes. All right. So we have this area minus this one, minus this one, plus this one, because we subtract these 2 times. Right. And that's it. This is the first property, and this is what we did next previous class. Now we continue with the second property. So if you remember, if we talk about, when we talk about the CDF on the one-dimensional case, we say that the limit of this function when n tends to infinity tends to 1, and the limit of this function when the x tends to minus infinity is 0, right? So in one-dimensional case, we have something like this. Right, so this is 1. We have something like this. Yeah, this is a CDF in the one-dimensional case. Now here we have the following. We have, of course, we have not f of x, but we have f of x1, x2, and xn. So we actually have three limits here. The first one is that the limit of this function when each of these x1 tends to plus infinity, x2 tends to plus infinity and xn tends to plus infinity, so they all tend to plus infinity, we see that the limit is 1. So it means that the probability that the first random variable, the second random variable, and the nth random variable is less or equal to plus infinity, of course, is 1. Okay. So, and the second property is that if one of them tends to minus infinity, so if the limit of this function, if xi, so for every I, that's right, different place. But the second property is that for every I, right, I is a number from 1 to n, the limit of this function for xi tending to minus infinity is 0. So the probability that any of these random variables is less or equal than minus infinity, of course, is 0, right? But be careful, because here, if we want this to be 1, we have to make sure that each of the variables here tends to plus infinity. If at least one of them doesn't tend to plus infinity, then this is not 1. I hope this is clear why. Okay. Yeah, and what else? Yeah, and this is the second property, right? And the third one, so the third property in the case when we have the one-dimensional CDF is that this function is continuous from the right. Right, so if we have, again, some CDF, this continuous CDF, then it should be continuous from the right, something like that. And here we have the same, so it means that this function is continuous from the right as well. So the limit of this function, when each of these variables tends to some number from the right, right? So x1 tends to x10 from the right, and xn tends to xn0 from the right. This is just the value of the function on these points, because this function is continuous from the right. And that's it. These are the properties of the CDF in the n-dimensional case. Now, in the same way, we have the following theorem or lemma. I think lemma, let's call it lemma. That for any function f from Rn to 0 and 1, such that properties, so any function f such that properties 1, 2, and 3 hold, is the CDF of some, you have unique probability distribution in Rn. So this is exactly the same. So when we had in the one-dimensional case, we have some CDF and for every CDF we had an unique probability distribution P. In this case, for every CDF so for every such function f such that we know that these properties hold, then it means that this function is the CDF of some n-dimensional probability distribution. Right. Okay. And this is also, so this is a consequence of the Carathéodory's theorem, right? So if you remember, so this is a consequence of Carathéodory's theorem. Of course, you don't have to know exactly what the Carathéodory's theorem is, but you have to at least understand the meaning of that, right? Again, it means that when we have a semi-ring, right? We had a semi-ring and some measure, some sigma finite measure on this semi-ring, then we have a unique measure on the sigma algebra. All right, but this is the unique. So this is like having the measure on the semi-ring, and this is like the measure on the sigma algebra, right? Something like that. Not exactly that, of course, but it's something like that. So that's the idea. Okay, so we have that. So we already know this function p in the n-dimensional case. Now we can talk about well, how to express it, right? So we have two cases, the discrete case and the absolutely continuous case. Exactly the same. So the discrete case, we already know it because we discussed that previous semester. I don't know if you remember that when we talk about the joint, did we talk about that? Yeah, the joint probability mass function. Yes, so we talk about the joint probability mass function, the joint PMF. Right, so in that case, what we had the following table, right? So we have, for example, psi, eta. We have some values for eta, you know, y1, 2, 3, and here x1, 2, x3. And here we had to write the probability that psi equals x1. So here, the probability that psi equals x1 and eta equals y1. Right, so we already discussed this. So the discrete case, when we have many different values, we just start talking about the joint PMF. Which lemma? This? Yeah, this lemma applies for both. Yes. So what do we have in the discrete case? Let me still write about that, right? So we already know this, right? So we are not going to solve exercises like this because we already know how to solve that, right? So, but somehow it's the following. So in that case, we have some x, some set x, which is either finite or countable, right? So in this case, we have that this is finite or countable, right? And for every point, right? In this case, a point is a point on the n dimension. So this is a vector, right? So this is actually a vector, right? Like this. For every vector here, we know that the discrete, so the PMF, right, or we can call it discrete density or joint PMF is just the probability of this vector, right? So we find the probability of each point, right? Because this is the discrete case. So like here, we have in this case the point x1 and y1, right? So we can define the probability of each point. Sorry, just a minute. Yeah, and we know that the sum over all possible x vectors, the sum of this is going to be just 1, right? So the probability of all the possible points give us 1. And that's it, right? So we already know that. So that's not interesting. Now, what about the absolutely continuous case? So in the absolutely continuous case, when we had only one variable, in the one-dimensional case, we define the density function, the PDF, the density, the density function. In this case, we're going to define exactly the same, but let's call it, I don't know how to call it. So this is, let's call it n-dimensional PDF. Right? So this is going to be a function on n variables. That's the difference. So how we define the PDF before? We define that the PDF is a function such that the CDF is the integral from minus infinite to x of this function. Right? And we say this function is called the PDF. Now this is exactly the same. So if there exists such function p that if there exists p of t such that f of x1, x2, xn is equal to what? To the integral n times, right? The how is the name of this in English? The repeated, the integral. I don't remember. So we have here n times, and this is from minus infinite to x1, minus infinite to x2, and from minus infinite to xn of such function t1, t2, tn, dt1, dtn. So if there exists such function, sorry, here we have a vector. We can write vectors. If there exists such a function that this is true, then we call this function the n-dimensional PDF. This is the n-dimensional PDF. We are going to call it just the PDF. Maybe in English there's a different name for this. I just don't know. So, but the name is not important, right? So this is the PDF. Okay, so it means that and this distribution, right, for this CDF is called absolutely continuous, just in the same way. So we have two different distributions. Well, actually three, right, because we have this the singular, but we won't talk about the singular. So we have the discrete distribution, and we have the absolutely continuous distribution. Again, when we have the discrete distribution, we talk about the PMF, the probability mass function of this distribution. So we found the probability of each vector here. And if we're talking about the absolutely continuous distribution, then we have to talk about the PDF, right? The probability density function, which is this one. And using this, we can find any probability that we want, right? All that you should know is how to find this integral. But you already know this, so there's not any problem.
So I hope you remember how to find these kind of integrals, because we will do that a lot. Okay. Okay. Now, let's talk about the properties.
Okay, I think we can continue. So, properties. So this is exactly the same that we did before. So, first property. So the first property should be, so what was the first property for the PDF? That for every Borel set, the probability that of that Borel set, so the probability that the random variable belongs to this Borel set is just the integral of the PDF on this Borel set, right? So this is exactly the same for every Borel set space, right? The probability of B will be just the integral of B of the function. Right? So this is the first case, the first property. Then we have the second property, in which what we have? All right, yes. So we say that the integral of minus infinity plus infinity of the derivative is 1. Right? We said before that, so this is exactly the same. But in this case, we have the integral over all Rn, right, of this function. We want, right? And finally, the third property is that we can find the density if we know the CDF, but only if the CDF is differential, right? So if F is differential, then B is just, so before we had just the derivative, right? But in this case, we have a function on n arguments. So we have what? Partial derivative. Is that the name? Of f(1) after x(n) of f. Right? So we can easily find B if we know f, but only if f is differentiable on these points. Right? So as you can see, it's exactly the same, but there are some things in which the one-dimensional case and the n-dimensional case can be very different than the first. Now, if we know all this, What else can we say? Yeah, that's it. So now we can talk about the random vector. Because again, we've been talking about the function, probability distribution, and so on, but without talking about random vector. So what is a random vector? A random vector is psi is a vector in which we have psi 1, psi 2, psi n. So this is a function. So a random vector in the same way as psi is a function from so what was psi? Psi is a function from omega to the set of the real numbers, right? So this one is a function from omega to the set of Rn. So that's the only difference. Such that this function is measurable. So this function on n arguments have to be measured. What is the meaning of that? Okay, so we have here omega and we have Rn. We have to make sure that for every model set here, so we have to make sure that for every model set, for every model set on the space, if this is psi, then the preimage of psi of this world set be an element of F, where F is the sigma algebra on this set omega. So in that case, we have to measure the space omega F. So if this function is such that this is true, then we call this a measurable function, and we can call this a random vector. So a random vector is the same way as a random variable is just a function. And yeah, and we can prove, but we're not going to prove it, but we can prove that if this is a random vector, then each of the components of this vector is a random variable. But this is not obvious. This is not trivial. Right? So how do we know that if this is a random function like this, how do we know that each of these things is a measurable function? That's not true, right? So if psi is like this, and this is a random vector, then by I, for every I is a random vector. So a random vector is just a collection of random vectors, right? Yeah. Great. So do you have any question, Lena? What exactly is confusion? Yeah.
So the mapping is from the circle to that.
From omega, yes. Rn. This is Rn, right? So this is the space. This is. So the only thing that we changed is that before we had R, now we have Rn.
Rn space.
Yeah. So for every omega, so for every elementary outcome omega, right? Because psi is a function of this, right? For every omega we have some, so this we have a number, real number, something like that. Now, for every omega we obtain some data. Collection of numbers. That's the only difference. So a random variable somehow is a random vector in one dimensional case. Any more questions? By the way, if we know that D, for example, is the Cartesian product of AB and CD, how do we find the double integral of D? The business theory, I think it's called from calculus. So we can just don't know the name of this in English. Graph, so I don't know. Well, this is right? Yes, no. X is from B, like that. Yeah. All right. So this is important. We will use this all the time. Also, because we have a function depending on x. Okay. Now we can move forward and we can talk about independence. Again, right? So how many times? So again, in which case two random variables are independent. So if we have psi and eta, we know that they are independent if the probability that psi is equal to something, right? So let's say that psi belongs to V1 and eta belongs to V2. It's the product. Yeah. In that case, so this is the definition of two random variables being independent. Okay. So we can do this for any number. Yeah, so we can do exactly the same if we have n random variables. Psi 1, psi 2, psi n are independent. If probability that psi 1 belongs to V1, probability that psi n belongs to Vn is equal to the product, right? From 1 to n of the probability of psi I belongs to I. It's exactly the same, but we can write, so look, what is the meaning of this P here? This P just, here we are writing this. The probability that, so this is just our way of writing this word, the probability of that. But this is not a function right now, but we can write this using the probability distribution. So in this case, we have a vector, psi 1, psi 2, psi n. So the probability distribution of this vector on this set is equal to the product of the probability distribution of each of them. 1 to n. So here we have the n-dimensional probability distribution, and here we have the one-dimensional probability distribution, right? So using the probability distribution, we can actually find if these random variables are independent, right? So here we have random variables, and here we have a random vector. Okay? Good. And we can write this in the following way. This is exactly how. Yeah, so as you can see, we have here BI, so B1, B2, and Bn. These are Borel set. But what if Bi is just the same, minus infinity times I? Then this thing from here becomes what? It becomes the CDF of this vector on this point. So this thing if BI is this, right? So it's like writing this B on minus 3 to 1 minus 3 to this is the same, right? But this, you know, this is the CDF. This is F of x1 and x2. Right? And in the same way, this is going to be A of psi I of xi. So we can write the following. This is a theorem. And we say that the random variables, so psi I and psi n are independent. In both directions, yes. If and only if f of psi 1 psi n and is equal to the product I want n of psi I. So now if we have some random variables and we know the CDF of these random variables and we know the joint CDF of these random variables, if the joint CDF is equal to the product of each of the CDF, then these random variables are independent. Okay, so we can find this, but it's hard to find this because we would have to verify this for every possible B1, B2, and here we only have the function which we already know. So if we are given with two random variables and we know the CDF of this random variable and we know the joint CDF, all we have to do to know if they are independent or not is to find the products. And if they coincide, then they are independent. And the same with density, but not problem. Okay. What else can we say? Yeah, we are close to finish this, but don't worry. So, what else do we need to do here? We need to talk about the marginal distribution. I think it's marginal distribution in it. We talked about that already. I don't know if you remember. So if we are given some vector, some vector, okay, some vector psi eta, and we know the CDF of psi eta. How do we know the CDF of psi? Right. So if we know the distribution of this vector, how can we know the distribution of psi? Yeah? No, the idea is not clear? Okay. Look, we have vectors and we have random variables. Right? Random vectors and random variables. If we have a random vector, for example, psi1, psi2, maybe we know the joint PDF, the joint CDF of this. So maybe we know this. So we know that we can know the probability that at the same time psi1 is less or equal than x1 and psi2 is less or equal than x2. Okay. So we're dealing with some vector, and we can find the probability that at the same time this is less than x1 and this is less than x2. Right? How do we find the probability that psi1 is less or equal than x1? Right? So that's not given here. So do you understand how I did? Sure? Yeah? No? So in the same, what is the probability that there are at most 5 girls in the group and at most 2 boys? Is one thing, and a different thing is the same. What is the probability that there is at most 2 girls in the group? So
given, we don't know.
Yeah, so if this is given, it doesn't mean that this is given, right?
But if we construct the graph and get the area, can't we just draw a line and everything to use that line at the end?
Okay, let's say that the probability, again, the example with the girls and the boys, so we have psi1 and psi2. This is 2 and 5, this is 3 and 9. This area gives us the probability that there are this number of boys and this number of girls. Now, if this is the area for that, what is the area for the probability that there are between from 2 to 5 boys?
So the whole thing, all the area.
Which area?
Both of them from the box.
So this? That's it?
Also beneath and above it.
Yes.
Yes, sir. All of this.
All of those. In all these cases, there are between 2 and 5 boys. The number of girls changes from minus infinite to plus infinite, but the number of boys it is 1, right?
So if you want to find at most 3. But you said, like, suppose that psi doesn't equal x1, suppose x1 is 3. There's going to be a line between 2 to 3. Well, you only need to be given.
Yeah, so we need to find all these areas.
Well, yeah, but it's going to be infinite.
Yes.
So,
How to translate that? Yeah.
Yeah, we just change one of the integral to
Yes, exactly.
There's going to be 1.
No,
Minus.
right? Because I told you before, and this is very important. Yeah. This is one only if all of them tends to plus infinity. If only one of them tends to plus infinity, then this gives us the CDF of the others. Everything. So, we call a marginal distribution a distribution that we got from some vector. So if we are given with this vector psi eta, then the distribution of psi that we obtain from here, we call the marginal distribution of psi, just like that. So what is going to be the, so yeah, it means that we have to find, we have to change this, if we want to find this, right? This is the, somehow, this is the probability that psi 1 is less or equal than x1 for any possible value of psi 2, right? So when psi 2 is less or equal to 1 infinity. Right? So this, all these possible values. This is going to be this, right? And formally, how do we write that? So this is the limit. So f of the marginal distribution of psi 1 x1 is the limit when x2 tends to plus infinity of f of psi 1 and of x1 and you know, right? So if we want to find the marginal distribution of psi, so this is the marginal, I'm not sure about the name, marginal distribution of psi 1. All we have to do is to find the limit. Right? And so formally we can write the following. Let me write that. Yeah, that if we are talking about probability distribution, then the probability distribution of VI, right? For every I, is just the probability distribution of R, VI, R. So we have here I minus 1 and so this is the same. I hope you can see. Right? So this, in this case, this is just the probability VI is, what is VI? It's 2 5. Right? This is the probability that we have 2 5 in X by the Cartesian product that we have R in Y. Right? So for every point here, so for every point between 2 and 5, we have every possible value of Y. Now formally, this is called formally the distribution is this. This is the marginal distribution of the marginal. Come on. So the idea is clear.
Now, what else do we need? Yeah, so we need that in the same way that we have this, right? We can find this using the PDF. So if we know that, if psi 1, psi 2, psi n are absolutely continuous random variables, then they are independent. So are absolutely continuous random variables, then they are independent if psi 1 and so I have here the joint PDF of this vector, and this is going to be the product of all the little PDF for psi I xr from I1 to n. So if I know that the random variables are absolutely continuous, all I can use is the probability density function. But that's only in the case when they are absolutely continuous. If we don't know that they are absolutely continuous, we have to use the CDF, right? Because this works for both cases, for the discrete case and for the absolute continuous. But of course, it's much easier to use this one if we know that they're absolutely continuous. And this is how we're going to check if they are independent or not. Okay. Good. We're almost finished. What else? We call this sorry. Yeah, we don't need that. Yeah, and the following is very important for you. So this is the convolution form. And the question is the following. If we have random variable psi and the random variable eta, and we know the probability, we know the CDF, so we know the CDF of each of these random variables. How do we find the CDF, the CDF of this random variable? Sorry, how do we find the CDF of this new random variable beside what's here? Right. So again, we have a random variable psi, we have a different random variable eta, and for each of them we know the CDF, and if they have, we know the PDF. How do we find the sum of the probability density function and the probability unity function for the sum of them? And the formula that we get is called the convolution formula. Convolution.
Like this, like drawing a table, and then there's a convolution formula together. Something that something called the sum.
Yeah, in the discrete case, it's also possible with the table, right?
Yeah.
We look at the, but this is the general case. So, how do we do that? I don't remember. So let me see.
Integration.
Yeah, we have to integrate something, but yeah, yes, okay. I see. Okay. Before that, what do we know? We know that both sine eta are absolutely continuous, and they are independent. So if we know that the PDF of psi is this, and the PDF of theta is this. What is the PDF of the vector psi theta? The product, right? Because they're independent. So if we know the PDF of two independent random variables, the joint PDF is just the product of these two PDF. So this is the PDF of this vector. Because they are independent. So what do we need to find? We need to find the CDF of this. So this is a new random variable we can call it. We need to find this. F of this one. X. Z. What is that? What is this by definition? Yeah. So this is the probability that 3 dimensions are equal to 0. No?
Yeah, it's very mindful that
A minus infinity. Well, before that, we have to think about this. Okay, let me show you. So look, we have this. What is this then? This is, let's use the PDF, not the CDF, right? So let's use the PDF. How do we express this using the PDF? So this is the integral over all such values, right? U plus B, such that they are less or equal than Z. U is for psi and B is for theta. Of what? Of the joint probability of the joint PDF. Now, so what is this? This is just this product. This is integral U plus B plus Z and U of psi U times U of theta B. So we have to integrate on this area. So we have this is U, this is B. We have to integrate on this area when U plus B is less or equal than Z. What if B is 0? What if B is 0, then U is Z. Z here and Z here. So U plus B equals Z in this line. And U plus B less or equal than Z, and then all the yeah. So we have to integrate for this area. So, so what do we have for U? U goes from minus infinity to Z, right? No, to minus infinity will go U and then minus B. Yes. So U goes from minus infinity. Okay? But no, U goes from minus infinity to plus infinity. Right? And V goes from minus infinity to Z minus U of this. Yes? When this calculus is not new. So let's look at the following. We can have here minus infinity plus infinity. We have we can take out y. So this function is on u. We can take it out, right? So this is inside u du, like that. And here we have the for minus infinity to z minus u d theta d dv. What is this? This is the probability that b is less or equal than z minus u. Yeah? So we have the density of b, and we are finding the integral from minus infinity to this number. So this is the probability right, that b is less or equal than z minus u. And what is the definition of that? So the probability that b is less or equal than z minus u is the CDF of b in this point. So all of this give us minus b plus b of b side u. We have n of so we have n theta z minus u dv. Right? And this is called the convolution form. So we can find the probability distribution of the sum of two random variables. So this, the formula is equal to this. So here we can write this side. Now, if f is differentiable, then we can find the derivative of this, and we can find the derivative of this, and the derivative of this one. The derivative of the CDF is the PDF. So, we can find the derivative here. That, and here also the derivative, right, in both sides. It is only if f is differentiable, and then we get that from here we get the PDF of this new random variable So the PDF of psi plus theta is equal to the integral from minus infinity plus infinity of this and this z minus 3. So this is just the derivative is going to be just like this. And this is actually the formula that we are going to use. This one. And that's it for the lecture.